Today, we're going to tackle a classic computer science problem, one that pops up all over the place. How do you build the cheapest possible network? Well, the answer lies in this really elegant process called Prim's algorithm. It's a fundamental tool for anyone who works with graphs or network optimization.
So, let's make this real. Imagine you're in charge of connecting a bunch of cities with roads. You have a map. You know exactly how much it costs to build a road between any two of them. Your job is to connect every single city, not necessarily directly, but so you can get from any city to any other for the absolute lowest construction cost. How do you even begin to figure that out?
The perfect solution we're looking for has a name, a minimum spanning tree, or MST for short. You can think of it as the network's bare-bones skeleton. It's got just enough edges or roads to connect all the vertices or cities. There are no loops or redundant paths, no cycles. And most importantly, if you add up the costs of all the roads you built, that total cost is the smallest it can possibly be. Okay, so how does Prim's algorithm actually find this perfect network skeleton? Well, it uses a beautifully simple and powerful strategy called a greedy algorithm. And that just means that at every single step, it makes the choice that looks best right now, without worrying about the future. It just grabs the cheapest, most immediate option available. You know, the best way to visualize this is to think about a tree growing. You start with a single seed, and then you just add the closest, easiest branch. Then, from that now slightly larger tree, you look for the next closest branch to add on, and you just keep going, one branch at a time. It's this very organic, incremental process.
Let's break down the playbook. Step 1. Just pick any city, any vertex, to be your starting point. It honestly doesn't matter which one. Step 2. Look at all the possible roads leading out from the city or cities you've already connected and find the absolute cheapest one that goes to a city you haven't visited yet. Step 3. You build that road and add that new city to your growing tree. And Step 4. You just do it again. Repeat that process. Find the next cheapest connection, add it, expand your tree until every single city is part of the network.
Let's walk through a quick example. So let's say we start at vertex A. The cheapest road from A is the one to B, with a cost of 1. Great, we'll add it. Our tree is now the set A, B. Now we look at all the edges coming out of both A and B. The next cheapest one to an unconnected vertex is from B to C, which also costs 1. So we'll add that. Our tree grows to A, B, C. And from this group, the cheapest path out is from C to D, which costs 2. We add that, and boom, everyone's connected. The total cost is 1 plus 1 plus 2, which equals 4. Done. Now, that seems almost too simple, right? It raises a huge question. How do we know for sure that this greedy, step-by-step approach actually gives us the globally optimal, cheapest network? Let's get into the secret sauce that makes this whole thing work. And this is the million-dollar question. It feels like a trick, doesn't it? Just picking the cheapest immediate option over and over again, you'd think that at some point you'd make a choice that looks good now but traps you into a really expensive path later on. So why doesn't that happen? Well, it turns out there's a powerful mathematical guarantee that's got our back. And that guarantee is called the cut property. Okay, stick with me here. Imagine you take all your cities and just divide them into 2 groups, any 2 groups you want. You've made a cut in the graph. The cut property proves that the single cheapest road or bridge that connects those 2 groups of cities has to be part of the final minimum spanning tree. It's always, always a safe choice to build that cheapest connection. And this is where it all clicks together. At every single step, Prim's algorithm is creating one of these cuts. The 2 sets are the cities already in our tree and all the other cities we haven't connected yet. By always choosing the lightest edge that crosses that divide, it's basically just using the cut property over and over and over. Every choice it makes is a mathematically proven safe step towards that perfect, optimal solution. It's brilliant. All right, so we know how it works, and we know why it's guaranteed to be correct. Now let's get into the nitty-gritty, the practical stuff, like how fast it runs, common things to watch out for, and some of those tricky edge cases. So the speed of Prims really depends on the data structures you use to implement it. If you have a dense graph where basically every city is connected to every other city, a simple approach is totally fine. But for sparse graphs, where cities have way fewer connections, it's much smarter to use something called a priority queue, often built with a binary heap.
Just think of a priority queue as a super efficient to-do list that always keeps the cheapest available road right at the top, ready for you to grab. This little optimization is what gives you that much more efficient O of E log V time complexity you see so often. And what about memory usage? Well, it's actually pretty light. Aside from storing the graph itself, you really only need a little extra space for each vertex to keep track of things like, have we visited this city yet? And what's the cheapest way to get here? So the space complexity is linear, or O of V.
Now, here is a huge point of confusion for a lot of people, mixing up Prim's algorithm with Dijkstra's algorithm. They look kind of similar, but their goals are totally different. Remember, Prim's is building a collective system, the cheapest possible tree to connect everybody. Dijkstra's, on the other hand, is like using Google Maps. It's finding the shortest path from one single starting point to all the other destinations. One is about infrastructure, the other is about routing.
So what happens if your graph isn't fully connected? Say you've got cities on the mainland and then some on an island with no possible bridge. Well, Prims will just build an MST for the chunk it started in. To handle that, all you have to do is check if there are any unvisited cities left, and if so, just start the algorithm again from one of them. What you end up with is a minimum spanning forest, basically a collection of the best possible trees for each separate group of cities.
Here's a cool and sometimes surprising fact. What if a connection has a negative cost? Maybe it's a subsidized fiber optic line that the government pays you to build. Well, while a lot of shortest path algorithms completely fall apart with negative weights, Prims handles them just fine. Since it's only ever looking for the next cheapest edge to add to its tree, a negative cost is just a really, really attractive cheap edge. No problem.
Now, Prims isn't the only game in town for this job. To really get the full picture, you have to compare it to its main alternative, another algorithm called Kruskal's.
The biggest difference between them is their whole strategy. As we've seen, Prims is like growing a single crystal. It starts at one point and expands outward, always staying connected. Kruskal's is totally different. It looks at all the possible roads in the entire graph, sorts them from cheapest to most expensive, and then goes down the list, adding roads as long as they don't create a loop. So it starts with a bunch of disconnected cities and merges them into bigger and bigger islands until it's all one piece.
All right, so let's wrap this up and boil it all down to the key takeaways. First, Prims is a greedy algorithm that builds one single connected tree. Second, its correctness is rock solid, guaranteed by something called the cut property. Third, its performance is typically O of E log V if you use a binary heap. And finally, remember its unique strategy. It grows a tree from one single point, which is different from Kruskal's, which merges entire forests together.
And that leaves us with one final thought. It's pretty rare that just making the simple, locally best choice at every step actually leads to a perfect overall outcome. Prim's algorithm is one of those special, beautiful cases where it does. So it makes you wonder, where else, maybe in computer science or even in life, might making simple, greedy choices actually lead to the best possible result? It's a fascinating thing to think about.